Hello, my name is Taylor Bacher, and this is Lab 2, Motion of a Falling Object. The purpose of this lab is to observe the motion of an object dropped from rest falling down, measure and analyze motion using tracker, create two computational models using Newton's second law, one with drag and the other without, and to compare two computational models and the experimental model to each other. From these, the results are that the more forces taken into consideration during a computational model, the more realistic and accurate it is. So this is why the model including drag and gravity were closer to the experimental model. Some quick background information is that the only forces acting on an object when falling should be gravity and the force of drag, and that the net force on an object is the sum of all forces. So in this case, F net equals force drag plus force gravity. This is known as Newton's second law. Below are also some more relevant equations. Now let's look at our experimental model. To set up the experimental model, I dropped a chapstick from a height of 2 meters, and then I used tracker to analyze the motion of the chapstick. In this case, the system is the chapstick and all other objects and forces are the surroundings. These are the initial conditions. These are the results from the experimental model. We found that the y component decreases as time increases and velocity is not constant. Now let's look at our computational models. We have two different computational models. The first one, the only force is going to be gravity. Here the system and surroundings are the same as the experimental, and drag is set to be 0, and F net is calculated using gravity and drag. A while loop using Newton's second law and the velocity position update formulas is written in the code. The initial conditions stay the same. For the second model, gravity and drag are included as the only forces. This has the same system and surroundings, except B is set to 0.005, the proportionality constant of drag found from trial and error. Rest of the code is the same. From our computational models, we see that both have a downward slope, meaning velocity is negative. However, the model with drag shows that velocity is not in a constant downward slope, so the acceleration must be constantly changing. Whenever we compare all three models, we see each one has a different behavior. This is due to different sources of error in the experimental method. However, because the model without drag just has gravity pulling down, it is falling faster than the motion of the object with drag, and the one with drag is going to be closest in similarities to the experimental one. Which model predicts a terminal velocity? Terminal velocity is the velocity when drag force is equal and opposite of the force of gravity. The model which depicts this is the computational model with drag. The net force in this case is 0. But what if the object is initially thrown? The terminal velocity is unchanged by an initial velocity. It's only affected by the velocity at which the magnitude of the drag force is 0 newtons. Overall, we have some sources of error. Tracking the object's motion using tracker causes human error, and there could be inaccurate measurement of distance and mass. There could be external forces, and our object was not very aerodynamic. From this, we can conclude that accounting for drag computed a more realistic model when predicting an object's motion when falling down, and multiple forces make up the realistic net force on an object.